In this lesson, we're covering solving polynomial equations. The linear factorization theorem says that if we have a polynomial, that polynomial is going to have factors. So that means that terms that we're going to be able to multiply. And those factors are going to be determined by the degree of the polynomial. Each of the factors needs to be written in the form x minus c, where c is a complex number. Complex number means that it could be a real number. It could also be an imaginary number. In the example that we have right here, we can see that we have an x to the third power. Because we have an x to the third power, that means that we need to be able to write it in 3 factors. That is the core idea of the linear factorization theorem. Based on the degree of the polynomial, we're going to be able to factor the polynomial in that specific number of factors. So if the degree of the polynomial is 20, then we need to have 20 factors. For example 1, we're going to factor the polynomial function. So we need to be able to put this in terms that we're going to be multiplying. Now, for this problem, we're going to do it by grouping. So I'm going to group the first 2 terms, and then I'm going to group the last 2 terms. I'm going to find what the first 2 terms have in common. We see that the first term doesn't have a number in front, so there's no coefficient, and the second number has a 3. So we are not able to factor a number from the coefficient, but we are able to factor the variable. This one has an x to the third power, and then this one has an x to the second. So I'm able to factor an x to the second power. If I factor out x to the second power, I'm going to be left with x plus 3. Then, from the last 2 terms, we see that this is a -4 and we have a -12. Only the first term has an x, so we are not able to factor out an x in this case. Now, we do know that -4 and -12 are both divisible by the same number, which is going to be -4, the greatest common factor between the two of them. So if I factor out a -4, I'm left with x plus 3. The goal of using grouping is that you're going to make sure that this and this matches. Because now that we have these two, they are exactly alike, we can factor that out. So when we factor x plus 3 from both sides, we're going to be left with x squared minus 4, and that's going to be our second term. So we factor the x plus 3, we put it in the front, and then we got the x squared minus 4 right there. Now, we have an x to the third, so that means that we need to have 3 terms, not 2. This one is in the simplest form, but we need to be able to simplify this. This is a special case, so you're able to simplify using the special case properties, but just in case, I'm going to go over the diamond. So we're able to look for 2 numbers, and when we multiply them, gives us -4. Since we don't have a term with an x, we know that that's going to be 0. So 2 numbers, when we multiply them, that gives us -4, but when we add them, gives you 0. That's going to be 2 and -2. That means that the factors for this section is going to be x plus 2 and x minus 2. we're just bringing the numbers from the diamond. And that's your answer. We needed to find the three factors. These are the three factors. The zero property states if you have an A and B and you multiply these two numbers and it equals 0, then either A is 0 or B is equal to 0. And let's put a couple numbers. So if we have, let's say A is equal to 7, and you have A times B is equal to 0, that means 7 times B is equal to 0, divided by 7, B is equal to 0. Or let's say you have B is equal to -4, then we're going to get A times B is equal to 0. So A times -4 is equal to 0. We know that A is going to be 0. That's how the zero property is applied. Let's apply the zero property. So we know that based on the property, if the first term is 0, then the whole thing is going to be 0. Or if the second term is 0, the whole thing is going to be 0. So we're going to put that x is equal to -2. So if we replace x with -2, we get -2 plus 2, -2 minus 5, that's equal to 0. So we get 0 times -7. And we know that this is going to be 0. We could also replace x with 5. If we replace x with 5, we get 5 plus 2, 5 minus 5, and that's equal to 0. And we get 7 times 0 is equal to 0. And we know that that statement is true. So if you are able to find one value that makes one of the factors a 0, the whole product will be a 0. Okay. For the next one, we're going to use -6. So we have t is equal to -6. So we have -6 times -6 plus 6, and that's equal to 0. So we have -6 times 0 is equal to 0. So this statement is true. If we were to multiply the first polynomial out, so let's say we have this one and we put it in standard form. If we multiply that polynomial, we get x squared minus 3x minus 10. So this just comes from properties of a multiplication of polynomials. Now, if I replace that with -2, we are going to get -2 square minus 3 times -2 minus 10. So this will give us +4, +6, and -10. So we have 10 minus 10, which gives us 0. So we see that if it gave us 0 for one of the factors, it's going to also give us a 0 in the actual polynomial. The fundamental theorem of algebra states if you have a polynomial, and that polynomial we're going to say f of x, and the degree of the polynomial is n, where it's going to be a number greater than 1, then anytime that you make that polynomial, that equation equal to 0, you're going to get at least, and that is the important part, at least one solution. And this solution can be a complex number. So the difference between this one and the linear factorization theorem is the linear factorization theorem tells you exactly how many factors, but they're talking about factors. Now, this one is telling you that you're going to get at least one, but you're talking about solutions, no longer factors. The corollary, it's derived from the fundamental theorem of algebra. So the fundamental theorem of algebra was proven, and we know that that is true. Now, this is like a product of that. And this one, it gets a little more specific. This is where you can put the fundamental theorem of algebra and you combine it with the linear factorization theorem. And it says if you have a polynomial of n degrees, now you're going to have n solutions. So this one tells you if you have x to the fourth, that means that you're going to have 4 solutions. If you have x to the 15th, then that means that you're going to have 15 solutions. One thing that you need to make sure that you understand are the solutions. The solutions are going to play a key role in this lesson. A polynomial, again, with the nth degree, is going to have a total of n solutions. That is using all the theorems that we have covered. Now, some of the solutions may be real numbers, and some of the solutions can be imaginary numbers. The thing is, imaginary numbers always come in pairs. You are never going to get one polynomial that you only have one imaginary solution. If you have one, automatically you need to have a second one. That's going to be your pair. So these are always going to come in even numbers. The complex conjugate theorem states if f is a polynomial function with real coefficients and you have a plus bi is an imaginary zero, then you also have a minus bi is also a zero of the function. So let's say a is a number and b is a different number. So we're not going to change the I because the I is going to be your imaginary number. But we can say that, let's say we have negative 4 plus 2i. The theorem tells us that if this is one of the solutions, that means that the only thing that we're going to do is change a sign to the imaginary part. So we are going to say that negative 4 stays the same, but negative 2i will also be a solution of that polynomial. Or if you have, let's say, 7 minus 3i, that means that the other solution is going to be 7 plus 3i. In some cases, you're going to get some solutions just with the imaginary part. So you may get negative 6i, and that means that the pair will be also 6i. For example 2 says the polynomial x to the fifth plus 3x to the second plus 16x plus 48 equals 0 has 5 solutions. We know that it has 5 solutions because the degree right here is 5. And now it says, can it have exactly 4 real solutions? So that means the total right here has to be equal to 5. But we know from the previous theorem that imaginary numbers come in pairs. So 0, it's an even number, so we have no pair. We could have 2, that is a pair, or you could have 4, that is 2 pairs. Now, if you have 2 imaginary numbers, then we have 3 real. If you have 4 imaginary numbers, then you have one real solution. The question was, can it have exactly four real solutions? The answer is no, because you could have 3, 1, or 5, but not only 4 real. You could have only 4 imaginary numbers, but not 4 real numbers. There's nothing else that we can put here. So we can actually just cross that out because we have nothing that we can put in that will add up to 5 with even imaginary numbers. The irrational conjugate theorem states that if you have a polynomial and this one has rational coefficient, we're going to say that A and B are going to be rational numbers as well, but the square root of B is actually going to be irrational. So if you have something like that, you're going to get a number A plus the square root of B. So you have a rational number plus an irrational number. If that is one of your zeros, then the only thing that you're going to do is change the sign for the irrational, and that will be the second zero. So if you were to have 3 minus the square root of 2, we know that 3 is rational, the square root of 2 is irrational, so what we're going to do is just change the sign, and we know that that will be the second solution. If we were to have negative 7 plus the square root of 5, then our answer would be negative 7 minus the square root of 5. The only thing that we're doing is changing the sign of the irrational portion. For this problem, we have to solve the polynomial. So that means that we are going to make the polynomial equal to 0. That is how we're going to solve for it. But before we get there, we need to factor it. So we are going to group the first two terms and the last two terms. So these two are going to be together. And you look for what do they have in common. So this one is an x to the third power, so x times x times x. And then this one is x to the second, so x times x. So from the first part, we're going to factor an x to the second because they both have that term. And we are going to be left with x minus 1. For the next portion, this is a 4x, and we have another 4 right here. So that means that we're going to just take out that 4, and we're going to be left with x minus 1. The idea, again, is that we're going to make this one and this one look exactly the same. Now that we have that, we're going to do x minus 1, that's what they have in common, and then I'm just going to write what we have left. X squared plus 4. And again, we need to make sure that we make all this equal to 0. This is where the 0 property comes into place. Now, you would think that you need to factor this one. But what happens here is there's no number that when you multiply by another one gives you 4, but when you add it gives you 0. They need to have opposite signs so they give you 0. In this case, we're going to split it and we're going to make x minus 1 is equal to 0, and we have x squared plus 4 is equal to 0. And we are going to solve it. We know that we only need one of them to give us a 0, so it cancels everything out. So we are going to add a 1 to both sides on this one, and we have x is equal to 1, and that is the first answer. We're looking for 3 answers because the exponent is 3. Now, for the next portion, we're going to subtract 4 from both sides, and we get x squared is equal to negative 4. You find the square root. When you're finding the square root, you're going to get a positive and negative, and this is where the complex numbers come in. Anytime that you have a negative inside the square root, that is going to be an I. So I'll make a little note on this. So the square root of -4 is going to be the square root of -1 and the square root of 4. So this is where the I comes from, and the square root of 4 is 2. So those are going to be your three answers. Now we have x is equal to 1, x is equal to 2i, and also -2i. So this is where you can see that how the conjugate theorem comes into place. You have two imaginary answers and you have one real one. Again, we're going to group the first two terms for this one. So 3x to the third plus 4x to the second. And then we're going to find this two. We're going to aim for the greatest common factor. So the greatest common factor between 3 and 4 is 1. They have no other number in common, so we cannot take out any constant. But for x to the third and x to the second, we are able to factor out an x to the second. And then we're left with 3x plus 4. So our numbers didn't change in this case. We kept the 3, we kept the 4. Now, if we pay attention to the greatest common factor between these two, it's going to be different than the previous one. Keep in mind that we're trying to make this section right here look like this. We need a 3x plus 4. So the first thing that we're going to do is factor out a negative. They are both negative and we need them positive, so I'm going to take out the negative. The second thing that we need to do is find the greatest common factor between 18 and 24. They're both divisible by 2, but if you factor out 2, you end up with 9x minus 12, and that's not what we're looking for. We're looking for 3x plus 4. So I'm going to factor out a 6. When you factor out 6, 3x, and -24 divided by -6 is going to give you +4. Now that you have this term and this term looking exactly alike, we're able to factor that out, and we have 3x plus 4, and we're going to have x to the second minus 6. We're going to now make this equal to 0. So we get 3x plus 4 is equal to 0. And we have x squared minus 6 is equal to 0. We're going to deal with the left side first. So we're going to subtract 4 from both sides. And we get 3x is equal to -4. And then we divide by 3. We divide by 3. X is equal to -4 over 3. Your answers can be fractions, and this is an example of it. And now, when we deal with the right side, I'm going to add 6 to both sides. And we have x squared is equal to 6. You're going to find the square root once again, and you get x is equal to plus or minus the square root of 6. Now, 6 doesn't have, is not a perfect square, so we're just going to leave it as that. It's going to be an irrational answer. So your answer for this problem, and I'm going to put it on the left hand side, it's going to be x is equal to -4 over 3, the square root of 6, and the negative square root of 6. So those are going to be the three answers that we need. The rational root theorem states that if you have a polynomial, and again, we have a sub n x to the nth power, so this is just a representation of any polynomial of any degree, and you need to make sure that you have integer coefficients. So all your coefficients are going to be whole numbers, positive and negative. Then if that's a polynomial that you have, you are able to find the solutions by using P over Q. Every rational answer of that polynomial, that means that any whole number, any integer, any fraction, you are going to be able to find it in the form P over Q. P is going to be the factors of the last term. So you're going to look at the last term and see what factors they give you. Q is going to be the factors of the leading coefficient, the first term. For this problem, we're going to list all the possible factors. So we're not going to solve the problem, we're just going to list all the possible factors. We know from our definition that P is going to be your last term. So this is P, this is Q. So to find the possible terms, you're going to look at all the factors. So the factors of P is going to be positive and negative 1, positive and negative 2, positive and negative 4. And the factors of Q are positive and negative 1 and positive and negative 5. So P over Q is going to be positive and negative 1, 2, 4, and that is just these numbers divided by 1. But now we need to divide 1 by 5. So one of our answers could be, again, positive or negative 1/5, 2/5, or 4/5. So the theorem tells us that these numbers are going to be the solutions for that problem. Those are your possible solutions. So now we're going to have to test this out. For this problem, we're going to be using the synthetic division and the rational root theorem to be solving for the polynomial. That's why it's equal to 0. So what we're going to do first is identify our P and our Q. So our P is going to be 20 and Q is going to be the coefficient in front. We have an invisible 1, so that is going to be your Q. The possible factors of P are positive and negative 1, 2, 4, 5, 10, and 20. And the possible factors of Q, in this case, is just positive and negative 1. So when we do P over Q, the numbers that we can get are positive 1, 2, 4, 5, 10, and 20, but also the negative one. So we have negative 1, negative 2, negative 4, negative 5, negative 10, and negative 20. And what we're going to do is we're going to make our synthetic division. So we have 1, negative 8, 11, and 20. And the goal is going to be getting a 0 as your remainder. If you get a 0 as a remainder, that means that you did it right, and that is one of the solutions. So we are going to start with the easiest number that we can start with is 1. So let's start with 1. 1 times 1 gives me 1. We get negative 7. 1 times negative 7 gives us negative 7. Now we get positive 4, and then we get 4. So in this case, we get 20 plus 4, and we know that that's 24. So our remainder here is not 0. So right here, this did not work. So when that happens, you're just going to cross that number because now we cannot use it. We know that that's not going to be the answer. and we're going to try a different number. So we go with synthetic division. We have 1, negative 8, 11, and 20. And now we just need to try a different number. Now we're going to try 4. We have 1 times 4 gives us 4, negative 4. Negative 4 times 4 gives us negative 16, which gives you negative 5, and this gives us negative 20. So in this case of 0, so in this case, this one does work. So we can circle that one because we know that that's going to be a solution. If it worked once, it can also work a second time. So you can test that number to see if it works again. But in this case, this is not going to be the case. Whenever you get to this point, you can actually write this in standard form when you have it as x to the second minus 4x minus 5, and you are able to use the diamond method, the quadratic formula. You can use different methods. For our purposes, we're going to finish this in synthetic. The next number that we're going to do is going to be 5. 1 times 5 gives us 5, a remainder of 1, and then we get 5, and our answer is 0. So we know that in this case, this was a valid number, so 5 also works. And the next number that we're going to try is going to be negative 1. So we tried 1, but we haven't tried negative 1. So we're going to put negative 1. 1 times negative 1 gives us negative 1, and we get 0. So this one also works. So we got 3 numbers that work, and we were looking for 3 solutions. We know that it has 3 solutions based on the degree. So we're going to write it as x equals 4, 5, and negative 1. Those are our answers. The instructions is to find all the solutions of the polynomial. In this case, our q is going to be 1 and your p is 48. So I'm going to list the possible factors vertically. So p over q. So all the different multiples of 48. So all the possible factors are 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. And we have the positive and negative of all these numbers. And we know that we only have those and there's no fraction because the q is 1, so we don't have anything there. I wrote it vertically just to save some space. Now, we're going to, once again, start with synthetic division. So we're going to write 1, negative 3, negative 34, and negative 48. The first number that we're going to try is negative 2. So we have 1 times negative 2 gives us negative 2, negative 5, and that's going to be positive 10, and that's going to give us negative 24, and we're going to get positive 48. So our remainder was 0, negative 2 works, so we have negative 2. That's our first one. In this case, that we already have only 3 terms, you are actually able to solve this problem slightly different. From synthetic division, we know that this is x to the second minus 5x minus 24, and we need to make this equal to 0. So we can approach these problems in different ways. The reason that we want to start doing this after you have 3 terms is that sometimes you're going to get imaginary numbers, sometimes you're going to get irrational numbers. So the numbers that you may be trying won't work. So for that reason, we are able to use different approaches. In this case, we're going to do it by factoring. So we're going to look for two numbers. Then when you multiply them, gives us negative 24. But when you add them, gives us negative 5. And that's going to be negative 8 and positive 3. So we're able to factor this into x minus 8, x plus 3, and this is equal to 0. So we get x minus 8 is equal to 0, x plus 3 is equal to 0. So plus 8, x is equal to 8, minus 3, x is equal to negative 3. So the answer to this problem is going to be x is equal to negative 2, the first one that we got from synthetic division. Then we have negative 3 and 8. This makes it easier so you don't have to keep testing numbers to see which one works, because in this case we had a large group of numbers that we could test, but once you have 3 terms, you can just use a different approach. For this problem, our P is 24 and our Q is 4. So we need to find all the possible values for our P over Q. So our factors are going to be 1, 2, 3, 4, 6, 8, 12, and 24. Those are the factors of 24. But now we also need to make sure that we're adding the fractions. The fraction is going to be 1/2, 3 over 2, and we also have 1 over 4 and 3 over 4. We are going to use synthetic division now, so we have 4, 16, 4, negative 32, and negative 24. And this is going to be a trial and error. You're going to try to look for numbers that are going to cancel. The first number that we're going to do is going to be negative 1. We have 4 times negative 1, negative 4. This is going to be positive 12, negative 12, negative 8. This is going to be positive 8, and that's going to be negative 24. Negative and negative will give me a positive, so we got a positive 24, and that means that we got a 0. We're going to test a different number. So let's try 2. We have 4 times 2, 8, 20, that's going to be 40. This is going to be 32, and we can clearly see that that number is not going to work out. So positive 2 is not working. So let's try again, but with a different number. And we need to keep using synthetic in this case because we are not able to put it in standard form because it's not quadratic yet. So we're going to try negative 3. So we have negative 12. That gives us a 0 right here. That is great. 0 times 3 gives us 0. We bring down the negative 8, and this gives us positive 24. And that is perfect. We get a 0. So when we put this in standard form, we get 4x to the second minus 8 is equal to 0. We're able to solve this one very straightforward just by doing inverse operations, or you can do the quadratic formula if you would like. In this case, what we're going to do is we're going to solve it straight. So we're going to add a to both sides. We get 4x to the second is equal to 8. divide by 4, divide by 4, x squared is equal to 2. And now we're going to find the square root. And when we find the square root, we have x is equal to plus or minus. 2 doesn't have a perfect root, so we're just going to put it as plus or minus 2. So the answer for this one is x is equal to -1, -3, and plus or minus 2. Those are the answers. In this case, we have a polynomial of degree 5. That means that we are going to be looking for 5 uh, different solutions. And we are going to do P over Q, and P over Q is all the factors, so P divided by Q. And the 1, 3, 5, and 15, and that is positive and negative. And now we also need to get all the fractions. We know that 10 is divisible by 2, 5 as well. So we're going to be getting all the different fractions. So 1 divided by 5, 3 divided by 5. We also have a 15 divided by 5 is just going to be 3, so we don't need that one. And 5 divided by 5 gives us 1, so we don't need that one. We have 1 over 2, 3 over 2, 5 over 2, and 15 over 2. We have 1 over 10, 3 over 10, 5 over 10 is going to be a, but we already have 1/2, so we don't need to write that one. And 15 over 10 is going to be 3 over 2, so we don't need 3 over 2 either. Now, we are going to have to do synthetic division at least a total of 3 times because we have multiple solutions here. And we're going to start by using the first one, which is going to be 10, 29, 4, -60, 2, and 15. And we're going to start with 1. We have 1 times 10 gives us 10. We get 39. 1 times 39 gives us 39. This is going to be 43. 1 and 43 gives us 43. And this is going to be 17. -17. So 1 and -17 gives us -17, which is -15. And we get -15 right here. That is going to be 0. If you keep trying numbers, you're going to see that all the numbers are going to get larger and larger if you're using whole numbers. So we actually need to start using fractions. And the fraction that is going to be our solution, and we're going to test out, is going to be -1/2. 10 times -1/2 is going to be -5. And this is going to be 34. When we multiply these two, we're going to get -17. We get 26. 1/2 times 26 is going to be -13. And this is going to be -30. -1/2 and -30 is going to be +15. And that's going to be our next zero. And our last zero using synthetic, again, we're going to have to use another fraction, and that's going to be 3 over 5. 10 times 3 over 5 is going to be 6, and this gives us 40. This is going to be 24, and that's going to give us 50. And this is going to give us 30, so our remainder is going to be 0. So now that we are there, we can actually write this in standard form. So we can rewrite this as 10x to the second plus 40x plus 50 is equal to 0. Now, these are very large numbers, so one trick that we can use is divide everything by 10. So that gives us x to the second plus 4x plus 5. We know that 0 divided by 10 gives us 0. And now we're going to be using the quadratic formula. So the quadratic formula is going to be negative b plus or minus square root of b squared minus 4ac over 2a. And using the numbers that we have negative 4 plus or minus 4 squared minus 4 times 1 times 5 and everything over 2 times 1. And we're going to simplify this using a calculator if you need it. When we simplify this, we get negative 4 plus or minus the square root of negative 4 over 2. And that is going to be negative 4 plus or minus 2i divided by 2. So we can rewrite this as negative 2 plus or minus I. So the answer to this problem, we have 5. We have x is equal to 1, negative 1 half, positive 3 over 5, and we have negative 2 plus I and negative 2 minus I. This is where the complex root conjugate theorem comes into place.